Well, I think it's time to start the next episode of our hydrogen series between Cardiff University and the University of Wyoming. And today we plan to have Kara Frostrom talking about policy, but unfortunately, due to emergency, Kara cannot present today. So we have our three amazing researchers here at Hydrogen Energy Research Center at University of Wyoming, presenting on various topics that we are very much interested in. And so you will have this fantastic lineup. First, Sheida will present on hydrogen storage in Wyoming, and then Dayana will talk about the economics of water for hydrogen. And then we'll finish this with engineering aspects of water use for hydrogen, and William will talk through his presentation. We also are planning to have a next session organized by Cardiff this time, and my understanding is that there's going to be COP updates. There are multiple updates that are coming from this fantastic conference. And then after that, we'll have a policy webinar reintroduced, and Kara will present after that sometime in February. So without further ado, Sheida, could you please start sharing your screen? Thank you so much.
Hello, everyone. I'm Sheida. I'm a research assistant at the Hydrogen Energy Research Center, School of Energy Resources, University of Wyoming. And today I'm going to tell you about hydrogen storage in Wyoming and what we're doing in our research center related to the hydrogen storage. But before going into the main topic, which is hydrogen storage, I would like to give you a brief overview on the energy production in Wyoming and its related CO2 emissions. In Wyoming, we are producing most of the energy from coal mining, and the other fossil fuels that we're using as a source of energy are natural gas, crude oil, and we have also some renewables such as wind, and we're also started to investigate the feasibility of hydrogen production. So Wyoming has been the top coal producing state since 1986, and we're producing up to 2/5 of all coal mined in the US. And in Wyoming, we are actually producing 12 times more energy than we consume. So the problem that we have in Wyoming actually is not related to energy shortage, but the problem is the CO2 emission, which is associated with the production of energy in Wyoming. So to be more clear about the problem of the CO2 emissions or how we can develop or improve this cleaner energy, we can see here that we are producing around 44 million metric tons of carbon related to the coal production, and we are producing around 9 to 10 million metric tons of carbon associated with oil and gas production. So as I mentioned earlier, the problem is not energy production, but it's the emission of carbon related to those productions, and we want to produce a cleaner energy than the and to reduce the emissions of those carbon. So in terms of hydrogen production in Wyoming, School of Energy Resources has two main projects related to hydrogen production. One of them is Blue Bison project, and the other one is Williams Southwest Wyoming Hydrogen. So these two actually are located in the southwest of Wyoming, and they involve production of blue hydrogen through ATR, autothermal steam reforming, and it's also the second project is about feasibility study of green hydrogen production in Wyoming. So as to move to the hydrogen storage, we all know that there are three main storage media for hydrogen. The first one is aquifers, the second one is depleted reservoirs, and we have salt caverns. So if we compare these three media for hydrogen storage, we can say that salt caverns are the best option because they have a long-term storage, and we have a larger capacity, and we have lower risk media for the hydrogen storage in subsurface. But there are other options also, and also because the salt caverns are not available geologically everywhere, we need to go through the other potentials for hydrogen storage, which are saline aquifers and also depleted hydrocarbon reservoirs. So in Wyoming, if we want to go through all the reservoirs which are available or all the aquifers, it will be a very large amount of geological storage media to look for. So we started actually with natural gas storage media. Why? Because the infrastructure is already available for storage purposes, and we are reducing the risk of hydrogen storage if we want to convert a natural gas storage media, which is already exists, to a hydrogen storage, because we are not actually storing hydrogen, pure hydrogen. And also the natural gas which is available in the subsurface can act as a cushion gas, which will be like a pushing or a pressure for the storage or for the production of the hydrogen during the production. And also we are reducing the CO2 emissions because we are not purely using the natural gas, but we are adding the hydrogen. So the main screening criteria that we are working on for the hydrogen storage in the depleted reservoirs or the aquifers are the technical screening criteria, economics, the health, safety, environment, and social sides. So in terms of technical, actually, we are studying the depth of the reservoir, the properties of the reservoir, how the fluid can flow inside the reservoir, what is the capacity. In terms of the economics, we are going through the infrastructure or the cost that is required to convert the infrastructure from natural gas storage to the hydrogen storage. And also we are looking for different opportunities, like to talk to people, for example, or to go through the regulations regarding the hydrogen storage, and also the health, safety, environment, which is another important aspect that we're looking for and we're investigating. So as we mentioned earlier, salt caverns can be very suitable for hydrogen storage because they are highly impermeable, they require lower cushion gas, and they have higher deliverability rate if we compare it to the aquifers or the depleted reservoirs. But in Wyoming, actually, we don't have a thick salt deposit or salt formation that we can create salt caverns in it. But we have another formation which is similar to salt, and it is called trona. Trona, as we can see here, is located in southwest of Wyoming, and it is in Green River Formation. So the trona beds that we have actually are thin trona beds. They are not very thick layers, and we need to overcome this challenge because we are going to create caverns, and we need to have enough capacity for the hydrogen. So for this purpose, actually, we compared the salt caverns with the trona or potential trona caverns, and we found out that trona that we have in Wyoming is viable in terms of depth and also areal thickness or areal extent. But the thickness is the main challenge that we need to overcome for the development of the caverns. In terms of solubility, trona is different from salt, so we need to consider this during the cavern development. And the creep behavior is also showing some differences, so we need to consider that in terms of the stability of the caverns. So for the purpose of investigation related to trona caverns, we are taking into consideration different aspects. And the first aspect that we're working on is the geomechanical aspect. So the objective of this investigation is to see how different factors can affect the stability of the cavern and also the design of the cavern. For example, the depth, the thickness, the mineralogy, petrophysics, and other different factors, how they will affect the development of the cavern and stability of the cavern during injection or withdrawal. So we are conducting experimental work and numerical simulation for this purpose. And in terms of experimental work, we are doing the creep test. And in terms of numerical simulation, we are using Flex3D to understand the stress distributions around the cavern, the strain distribution, and how much is the allowable pressure, the minimum and maximum allowable pressure inside the cavern. Another aspect that we're considering is the geochemical part, and the study objective for this actually is how the pore size distribution actually is changing when we are exposing the trona to hydrogen. And also we want to know if hydrogen can go through the trona rock, or the trona can actually act as a sealing for the hydrogen that we are going to store inside the caverns. So as I mentioned, we considered the geochemical and geomechanical aspects, and we compared salt and trona caverns in terms of hydrogen storage. And also we are going to investigate the effect of impurities inside the trona cavern, inside the formation itself, or as an interlayer between the trona layers, and on geomechanical aspects, and also how they will affect the stability or long-term storage of hydrogen. In terms of the geochemical aspect, we are comparing salt and trona in terms of reaction between hydrogen and the minerals that we have in these formations. And also we are investigating the effect of cushion gas on pore size distribution. So as you know, we have the natural gas, sometimes as a cushion gas or other gases, and we have hydrogen. So we want to know how these gases will affect the pore size distribution of the trona. In terms of economic aspect, we are analyzing the economic viability of trona cavern construction in Wyoming. So of course, we are producing trona as a valuable mineral, and we want to use the caverns which are already left after production of the trona. And these should be studied carefully in terms of economic aspects. And also we are evaluating the hydrogen transportation and storage, and like how we can have a link to other places or the end use of the hydrogen. In terms of regulatory aspects, we are preparing an overview of regulatory and tax regulations and the challenges that we have in terms of storage. And also we're investigating the regulations of solution mining of caverns and how we can, like how the regulations fit into the development of the trona caverns. So this is about what we are doing in terms of hydrogen storage in our center. And if there is any question, I will be happy to discuss.
Yes, we'll have time for one question right now, and please submit them through the Q&A box. After each presentation, we'll have time for one question, and then we'll go to a general discussion. Well, if there are no questions, let's go to the next presenter, and Dayana is next.
Hi, everybody. My name is Dayana Zhappassova, and I'm an economist for Hydrogen Energy Research Center in the School of Energy Resources. And today I will be talking to you about water and hydrogen. So let me go ahead. There we go. So some background, why do we care about water issues in hydrogen production? Because hydrogen production, like all forms of energy, requires various amounts of water, depending on the mode of production. And water is a scarce resource across the world, especially in the arid Western United States. We get our water in the form of groundwater, precipitation, snow and ice fields, and then water vapor in the atmosphere. However, water availability varies greatly depending on the distribution of annual precipitation, and given climate change, that annual precipitation patterns are highly getting more and more variable. So we need to really consider our water resource when thinking about hydrogen production. So in terms of Wyoming location for water availability, we're actually located in a pretty good spot when it comes to natural water availability. Wyoming is situated along the Continental Divide, and it is a headquarters of 4 major river basins: the Missouri-Mississippi River Basin, the Green Upper Colorado River Basin, that Pacific Northwest houses Snake Columbia River Basin, and then the Great Salt Lake River Basin. So geographically, we are in a pretty good spot when it comes to our water availability. So how much water does Wyoming have? So on average, about 17 million acre feet of water is produced on Wyoming land area, 70% of which is surface water supply coming from the snow. We do also have access to groundwater, and it is distributed throughout the state with variable quantities. And it is estimated about 10 million acre feet of groundwater that is found in alluvial aquifers, and 3 billion acre feet in bedrock aquifers. However, groundwater use is a delicate matter because it is very scarce, and the rate of recharge is actually quite slow, of about 1 to 4 million acre feet per year. So we have to be careful when we consider using groundwater because of the dynamics of how that water is getting recharged. So looking at Wyoming, as you can see from this graph, this shows the percentage of Wyoming in each drought category by week for the last couple of decades. As you can see, Wyoming, the drought category ranges from dry, abnormally dry, to extreme conditions. So there is a cyclical pattern when it comes to water availability and that recharge that I was talking about in the last slide. So we have to think about alternative water uses and how we manage our existing water uses. So if we look at this graph, this showcases how we do use our existing water supplies. So about 95% of water we're using for irrigation purposes. So the large majority of our water is used for purposes of irrigation, and the remaining 5% is distributed among these other not much less important uses, like the public supply, the potable uses, which is your domestic residential water uses, livestock, mining, thermoelectric power, and aquaculture. So when we consider our existing water uses, we have to understand what our competing water uses are and kind of the value that we generate from all of these other competing water uses when we talk about potential water use for hydrogen production. So thinking about potential water use and hydrogen production, like I've already mentioned, all hydrogen production pathways include various amounts of water requirement. And actually, my colleague William Lawler is going to talk to you in more detail about particular processes and water requirements. But these are the particular processes that we are considering: coal gasification, biomass, natural gas reforming with carbon capture, and water electrolysis. So hydrogen, despite maybe some public views and perceptions, is not unique when it comes to requiring water for production. In fact, about 31 billion meters cubed of water is required for fossil fuel energy production. And that, compared to, again, irrigated agriculture use, is a fraction. As you can see in this graph, about 1,000 billion meters cubed is required to support the agriculture sector in our in the world. And a projected global hydrogen demand is about 2.3 gigatons per year. And that should require about 21 billion meters cubed of water, which is about 33% less than the existing fossil fuel water energy water requirements. So, like I said, water requirement for hydrogen production is absolutely not unique. And despite some opinions and perceptions, it's not significantly larger than the current water uses that we already experience. So let's consider an example case of 500 megawatt electrolysis facility. It is capable of producing about 70,000 tons of hydrogen per year. And water electrolysis water consumption can require 9 to 16 kilograms of water for every kilogram of hydrogen produced. And there is about 6.5 kilograms of water per kilogram of hydrogen that is required for supporting purposes like cooling, for example. So that would require about 11.4 million barrels of water for that particular case. So let's consider, because we've talked about different considerations when it comes to tapping into our freshwater and groundwater resources, we were thinking about, what about the produced water? So a case for beneficial reuse of produced water, specifically for hydrogen production. Produced water is water in the underground formations that is extracted as a byproduct during oil and gas production. The thing that we have to consider is that it is highly saline, so it has a lot of impurities and total dissolved solids concentrations. So it is brine water, which will require, of course, considerate treatment before we were able to use it. Majority of produced water today is treated as waste and is injected into deep underground disposal wells, or it's released in surface evaporation ponds. So a lot of operators, it's actually a cost for operators to dispose of that produced water, because currently we're not reusing it. So if there is an opportunity here to treat this water in an economical way, that could be a potential resource for us moving forward to support the hydrogen economy. So nationally, about 91.5% of produced water is injected. About 44% is injected for enhanced oil recovery, 38% injected in non-commercial disposal wells, 10% is injected in commercial disposal wells, which means that operators have to pay a fee in order to inject that produced water. And the remaining water is just discharged. Very few or very little percent is reused. Currently in Wyoming, we're not reusing it, but in other places like Texas, some of it is reused within the oil and gas operations. So how much produced water is generated? Is there enough to support the future hydrogen economy? Like I mentioned before, produced water is highly tied to production of crude oil and natural gas. Between 2012 and 2017, crude oil experienced a net increase of about 51%. Natural gas increased at about 18%, the production volumes, and produced water, the net increase was about 15%. As you can see, between 2017 and 2021, the growth of production in crude oil, natural gas, and produced water slowed down. However, the ratio between the produced water production and crude oil and natural gas remained at about 3.3-fold relationship. So this graph over here, this table, presents volumes of produced water in Wyoming. As you can see, total volume of produced water is about 1.6 billion barrels per year as of 2021. And the conventional formations, conventional production of crude oil and natural gas accounts for a larger share of that produced water production. 88% comes from oil production, and about 12% is associated with natural gas production. We have documented a loss of about 64 hydrocarbon producing wells. However, the volumes of produced water, just looking at those scales that we've talked about earlier, is quite significant. So it is a significant cost to operators to have to think about ways of managing that produced water. So how do we manage produced water in Wyoming? This data comes from the Wyoming Oil and Gas Conservation Commission. And as you can see, about 85% of produced water is currently injected for enhanced recovery, and about 15% as of 2021 is injected for disposal by the operators. So currently 0% is reused within or outside of oil and gas industry, once again, as of 2021. So, it seems like that there is a potential in the future to think about how we can tap into that resource and reuse it. So what are some considerations when we have to think about produced water reuse? So of course, local conditions play a huge role when it comes to thinking about how we're going to manage our produced water and if we will be able to reuse it. Geologic characteristics are very important. It is highly variable. The produced water is highly variable in regards to its salinity and its quality. In Wyoming, we actually have pretty clean produced water compared to other areas. Like we run about 10,000 folds of total dissolved solids concentration, and in comparison, for example, with Permian, which runs 10 times higher. So we do have a pretty good potential in Wyoming to be able to save on some of those treatment costs. The, of course, profile of regional water supply and demand plays a big role. If there is a lot of fresh water availability, it might not be competitive to pay an additional fee to treat the water, and it might not be competitive enough for reuse. However, just considering in the long run projections of the variability of precipitation patterns and just the scarcity of water as a whole, that constraint would be less binding. And then, of course, the cost and availability of permitted underground injection control disposal, the UIC disposal. There are actually competing uses for Class 6 disposal wells, just subsurface in general, with the introduction of carbon capture and storage. So depending on the value of that particular subsurface and how that value is going to change over time, that might create a constraint in the way that we dispose of our produced water. And of course, taking into consideration the risk for seismicity also plays a large role because it increases the risk for earthquakes. And then the envisioned end use scenario, of course, plays a big role depending on the intended use of produced water. There's going to be different considerations with regards to the treatment and just the perception. Public perception is a very important aspect of being able to tap into that produced water resource, just from a perspective of whether or not it's clean enough for potable uses. There's always that kind of looming perception of not wanting to drink brine water, which of course is a valid concern. So, like I've mentioned previously, there is a tremendous variability in the physical and chemical characteristics of flowback of produced water, and that variability comes from not only geographic location, but just the schedule of production operation. Like earlier flowback water tends to be cleaner than the later, so there has to be kind of there's that variance in that chemical composition. So there's several criteria in terms of widespread adoption of that water recycling of produced water. Of course, it has to be economically feasible in terms of the treatment costs. These days, that's the most variable component to the cost of producing or operationalizing that produced water is the treatment costs. And then other things like transportation costs, just kind of the proximity to the production site. Those aspects would affect, of course, the final cost of being able to incorporate this produced water into our production. So let's take a look at this table. This is an example cost breakdown to the operator. So it costs about 15 to 60 cents per barrel on average to source ground or surface water for an operator for oil and gas production. There's additional storage and transportation costs, which of course vary with the distance for the shipment. However, the disposal costs are about 40 cents to $1 per barrel on average these days for the operators. So the operators do pay a significant amount to be able to manage that produced water. So depending on how other conditions align, there might be a potential to make it feasible for operators to choose to sell that water after potential general treatment or advanced treatment practices for other uses like hydrogen production in the future. And just in general, one of the major considerations, like I've alluded to before, are social pressures, because water is a pretty touchy subject in the West. We are, of course, everybody cares about being able to have steady access to potable water uses. So we have to kind of work with the public and educate on the really the amounts of water that the hydrogen economy that would require, and kind of how it fits into the competing uses, and kind of overcome the stigma that there's an abnormally large quantity and proportion of water that would be required for hydrogen production. So with that, I am open to a question. Thank you, everybody.
There was a question, Dayana, which both Will and I kind of addressed, but maybe you have something to say in addition, because you mentioned that steam methane reforming or autothermal reforming for hydrogen production, and the question is, why bother with that? Why not just do electrolysis production of hydrogen?
Well, the basic, I would say that the major considerations at the moment is making hydrogen production feasible. And because we are currently relying on fossil fuels as our source of energy, we have to think about the transition towards that hydrogen economy. And the electrolysis, as far as I see it, we're wanting to move into the most sustainable and clean ways of producing hydrogen. And, our global mission is to reduce the carbon footprint that we as a society emit to mitigate climate change. So water electrolysis, of course, is the cleanest way because it doesn't produce CO2 emissions. However, there is, there's a caveat that if that electrolysis process is supported by renewable electricity generation, that is when it is truly, quote unquote, green. So in reality, if we are using, fossil fuels to generate electricity to support electrolysis, there's still that carbon footprint that is being generated. So we have to think of ways of kind of mitigating carbon emissions with the processes that involve fossil fuels. And from a perspective of, ATR and SMR, just with the way that we've been doing it so far and the economics and the infrastructure that is present in the moment, there's I would say, transition benefits to be able to, still generate hydrogen and still be able to use it in like fuel cell technology, but and like in the feasible capacity, right? Because the main consideration is whether or not the costs align for us to be able to do that. And with ATR and SMR, since the infrastructure is already there and the processes are well established, those costs are lower. So that's kind of the way that I see it. And maybe you and Will can have more to say about that.
And we can save it to maybe for discussion as well. But thank you for your answer. Then there's one more question that's relevant. I think we should address this. Could you touch briefly on the water rights in Wyoming? Is there any contentions between neighboring states? Again, not to go too much in detail. We can save for a longer discussion, but just briefly touching on that.
Absolutely. So it is a very important point. I'm glad that you brought it up. There is an additional regulatory constraint when we think about getting or claiming junior water rights in Wyoming in the Western United States, because our law and regulatory structure is first come, first serve. So basically, water rights have been allocated and spoken for quote unquote beneficial uses, which, like, I've showed earlier in the graph, a large portion of it comes for, agriculture, municipal uses, the domestic uses. So basically all of those different avenues have established water rights. And to be able to apply for new water rights in light of technological change, like with hydrogen production, is very difficult because, just because of that regulatory structure. So that's why we're thinking about just potentially tapping into that resource of produced water. There hasn't been established legislature in terms of how we will regulate that produced water, because currently it is considered as waste rather than as resource. However, as we step into this new economy, and if economics will allow us to tap into that produced water as a resource, there will have to come developments in our regulatory structure of being able to kind of regulate the uses and the rights and how it's generated in relation to mineral rights.
Very good, Dayana. Thank you so much. So next one is Will.
All right, can everyone hear me?
Yes, we can.
Let me go and share my screen real quick. No. Okay, perfect. Good morning, everyone. Thanks for coming to the webinar. So I will be speaking on the water use and hydrogen generation today. And so we'll just jump right into it. So firstly, we're just going to kind of go over the quick overall balanced equations for three different methods: electrolysis, steam methane reformation, and autothermal reformation. As we can see, electrolysis is a very straightforward process. It's one step taking water and splitting it into its constituent parts of 2 parts hydrogen, 1 part oxygen. Steam methane reformation is a 2-part process. You have your steam methane reforming part, which takes your methane and your water, and you create a product of hydrogen and byproduct of carbon monoxide. And in order to get rid of that carbon monoxide, you're going to want to do a water gas shift. So you're going to take an additional water to add that oxygen molecule to the carbon monoxide and create carbon dioxide, creating an additional hydrogen as well, taking advantage of an extra hydrogen yield. And as you can see, your overall production is 1 methane, 2 parts water, and you're creating 4 parts hydrogen and 1 part CO2. For autothermal reformation, it's a very similar process, except you're also taking advantage of a partial oxidation to create a higher yield of both hydrogen and carbon monoxide. But because you have carbon monoxide, again, you're still going to want to do your water gas shift to convert that from carbon monoxide to carbon dioxide. And as you can see in your overall reaction there at the end, you have your 6 parts water, 1 part oxygen, and 4 parts methane, yielding the highest hydrogen yield of the 3, as well as 4 carbon dioxide. So kind of looking at the overall water needs for each of these 3 methods, we're going to split it down into, again, electrolysis, steam methane reformation, and autothermal reformation. We can see that electrolysis has the highest water requirement, purely as reactant, not any supporting amenities. It requires 8.9 kilograms of water per kilogram of hydrogen produced. Steam methane reformation, taking advantage of that methane, splitting off those hydrogen molecules from the methane, significantly decreases that water yield down to 4.5 kilograms per kilogram of hydrogen produced. And autothermal reformation, taking advantage of that partial oxidation, decreases it even further. The total use is a little bit higher. This will be including all amenities used, such as your cooling towers or heat exchangers, or loss in your gas separators or pressure swing absorptions. As we can see, again, electrolysis is still the highest with 11.9. Steam methane reformation is 11, and autothermal reformation is 9.8 kilograms of water per kilogram of hydrogen produced. On the right-hand side there, you can kind of see a visual graph representing it. And this is, just for reference, 10,000 kilograms of hydrogen produced per hour. You can see how much water is required, methane is required, and oxygen is required for each of the 3 methods. All right, so I'm going to go into electrolysis real quickly. Just the most commonly known forms of electrolysis include alkaline, proton exchange membrane, and solid oxide. There are many others, but these are the three main that dominate the industry. As we can see here in the bottom right-hand corner, we have a block flow diagram. Excuse me. And we've got the three areas labeled, and the red is going to represent areas of absolute water loss. The blue will represent areas where water is being converted, and the red is, absolute water loss. Whoops. So, of course, you have your water purification unit. If you are using produced water, you're going to want to expel any brine that you have that's oversaturated and that can't be used. Once you have your DI water, that's going to be fed directly to the electrolyzer stack, where your water will be converted into its constituent parts of oxygen and hydrogen. And lastly, you're going to lose a small amount of water in that gas separator. Although the more I'm looking into this, that number is very negligible. It's probably in the area of one part per 1,000, or if you're using a dryer or water trap, it could even be down to 1 part per 100,000. So it's a very, very small amount, but you are indeed losing water in that gas separator. Another area that you could potentially be losing water is your heat exchanger or your cooling tower, but we will go into that in just a little bit further. So I'm going to go ahead and kind of group in SMR and ATR, steam methane reforming and autothermal reforming, into two, just because they are so similar, but of course I'll explain some of the differences. But just going over a block flow diagram of our steam methane reforming, of course, we are having our absolute water loss in our water purification unit. And then we have our conversion loss in our steam reforming and our water gas reforming, our water gas shift, where water is, being converted to carbon monoxide, hydrogen, and of course, where it's being converted to carbon dioxide and hydrogen. Again, just like the gas separators, we're going to have a very small amount of water loss in pressure swing absorption. This very similar numbers. It's almost negligible, but with a dryer or a water trap. However, of course, there will be some water loss that occurs in your pressure swing absorption. Another area that you could possibly be losing water is your carbon capture system. This depends. Most commonly used, it'll be an amine-based system, and there will be quite a bit of water loss in your scrubber. However, there are other methods that use less water, if that is your concern. I just have a general autothermal reforming block flow diagram here as well. As you can see, it's very similar to the steam methane reforming, but of course, we also have our air separation unit to include the oxygen straight into the autothermal reformer as well. So just kind of a quick recap of what we saw there. Where we're losing water in steam methane reforming and autothermal reforming is the water purification unit. Our reactors are steam, autothermal, and water gas shift reactors. The pressure swing absorption units, the heat exchangers in our cooling towers, and our carbon capture systems with the scrubbers. So I'm going to go ahead and just describe quickly the three types of reactors that we're using and how much water is being lost roughly in each of them. So the first one being that steam methane reactor. Within it, we have a reaction of steam with methane in the presence of a catalyst produced hydrogen and carbon monoxide. Autothermal reactor is very similar, of course, with that partial oxidation reaction taking place as well, converting steam, methane, and oxygen into carbon monoxide, and then later into carbon dioxide and hydrogen. In our water gas shift reactor, we're converting that carbon monoxide into carbon dioxide. Again, most of this kind of was explained a little bit. So how is the water lost? It's lost in the form of consumption or conversion. Water is used as a reactant to split into its constituent parts to form hydrogen, carbon monoxide, and carbon dioxide. Now, these reactors, from what I'm seeing, aren't perfect in converting everything from water to the desired product. So sometimes you may have a small conversion loss of about 5 to 30%, or you have a conversion efficiency of 70 to 95%. Now, in the pressure swing absorption, This is going to separate gas using an absorption, using an absorbent material such as zeolite. The pressure alternates from high to low between towers, allowing one gas to absorb the material while the other is released. And kind of very similar to that gas separator, the water is just going to be escaped through the oxygen or the hydrogen. It's going to be small traces amount that escape through those outlet gases. So in our heat exchangers and our cooling towers, there's going to truly shouldn't be any loss within the heat exchanger itself. The way most commonly the ones that you'll see are the plate heat exchangers. They send two fluids through a series of plates and pipes in a counter current motion to allow heat transfer via conduction or convection. So this, for the most part, is a closed loop system. There shouldn't really be any water loss unless there's a leak. Where that's really going to happen is where you then need to cool that now heated water. And so it'll be sent oftentimes to a cooling tower. And within the cooling tower, as we can see, you're going to have your small loss to evaporation, drift, bleed off, or blow down. Of course, you also have your overflows, splash out, filter backwashing and leaks. How much water loss is that going to account for? It's going to be roughly 8.5 kilograms of water for every metric ton that's cooled, 1% of water for every 10 degrees Fahrenheit of water that's cooled. Now, the neat thing about that is it's when we run the numbers, it's really not too much that's being lost. The largest losses occur between evaporation, blowdown, and a very, very, very small marginal amount of drift, which really only requires about 3% of your current full cycle makeup water. The other 97% can usually be recycled. So some ways that we can minimize our water loss is improving the water purification methods. I didn't go in too much into detail into this, but for our current produced waters, we've had estimates of about 66% purification, purging the other 33%. So obviously there's a lot of room for improvement there. The reactors, there's not too much we can do. The law of conservation of mass states there is no way to be more effective at transforming water into its constituent parts. However, of course, if we can increase that conversion yield so that a higher percentage of the water is being turned into hydrogen, that would help. And of course, also using alternatives such as methane can decrease the need for water, and use other reactants as alternatives. Pressure swing absorption is, again, a very negligible amount. The water can be sent through a secondary pressure swing absorption, though, is one method, or a gas separator, or a second gas separator. As I mentioned, a water trap or a dryer. These are all ways of collecting that last little bit. And so if we're very stressed for water, we could go ahead and do a second system just like that. And then for our cooling towers, water capture devices placed above that collect the water that has escaped through a series of HVAC systems and fans, increase demisters area, recycle, and purify the bleed off of wastewater. Sorry, my throat is drying up. So two more methods that we're going to go over really quickly are coal and biomass gasification. This is mostly going to be the emphasis on electrolysis and steam methane reformation and autothermal reformation. So we're just going to go over these fairly quickly. Coal gasification has an overall balanced equation of 3 carbon. This is oversimplified because as you can see, you've got your lignite, bituminous, and subbituminous coals that are incredibly more complex forms of coal. They end up being something like C197H94036. As you can tell, way more carbon and hydrogen and even a little bit of oxygen in there. But the common shorthand is the 3 carbon and oxygen and 4 parts of hydrogen will yield 3 parts carbon dioxide and 4 parts hydrogen. So as we can see, that's not a super great system, but of course there is a way to create hydrogen using coal. Biomass gasification. There's multiple ways that you could do this. Common forms include wood residuals, agriculture residuals, switchgrass, algae, municipal solid waste. Almost anything that has biomass and hydrogen can be used in a biomass gasification process. Right here, we just took one example, kind of somewhere in the middle of efficiency of algae. As we can see, we've got this long chain right here, including 6 carbon, 10 hydrogen, and 5 oxygen, combined with 2 parts of oxygen and 12 parts of water, is going to yield 10 parts of carbon dioxide and 19 parts of hydrogen. So for these kind of 2 methods that we've got going on, the coal gasification process requires 8.9 kilograms of water just as reactant. Biomass gasification is significantly better at 5.6 for specifically algae. Of course, there's lots of other methods that we could get into. Now, coal gasification gets significantly worse when we take into account for our supporting amenities as well. This can be bumped up all the way to an average estimate of 26.5 total kilograms of water per product of hydrogen and 15 kilograms of water for algae. So significantly better than the biomass gasification. So kind of some conclusions that we've had so far, and what we'd like to see moving forward is ATR requires the least amount of water in its process, but has a drawback of the highest methane demand. So unfortunately, yeah, that is a concern to be considering when we're looking at our carbon capture system as well. The fortunate thing is most water that's used in these supporting amenities or not being used, not being consumed directly, not being consumed directly can be used in a recycle stream. Another key takeaway is that autothermal reformation has the potential to be very environmentally friendly with, of course, the correct carbon capture systems in place so that we can be carbon neutral. And then lastly, some of the things we'd kind of like to look into forward or investigate deeper are water purities required for each method and device. And we also begin to do a deeper investigation into gasification and pyrolysis methods, because those are pretty surface level right there. And so that is the end. Does anyone have any questions?
Thank you, Will. Excellent presentation. Let's take a look at the question session. There's a series of questions of coupling nuclear reactors with hydrogen production, which is relevant. It's a good way to do things, but there are 2 concerns, and the reason why we do things here, and I'll address, is that we are looking at available technologies that we can use today and maybe tomorrow. And this is what this survey is about, where we are looking at existing technologies, sort of state of the art, and also maybe looking a little bit far ahead into the future, a little bit in terms of the research level that is available to become commercial. So we're not looking at cutting edge technologies that are not being proven in the field. And so that is the reason for us to do the survey, because the water is a precious resource and it needs to be preserved. And so we want to make sure that the technologies that we're using today, we can educate our stakeholders on what are the best way to preserve water in our region for hydrogen production. That's basically the main reason why we did this survey and why we did this study. Of course, there are maybe better technologies are coming up, but their terror level will not allow them to be even tried in the field in the next 10, 15, 20 years. And then we'll see. Once they're available, we'll see. But today, this is what it is. So do we have any additional questions? Oh, there's well, if we don't have any additional questions, I think we can adjourn, and we will return in the next month. And this time, this is going to be Cardiff University, who is going to be the organizing party behind the next episode. This is going to be COP update, and I think will be great to see you all in the next session. Omer, do you have any closing remarks?
No, I think fantastic presentations. I learned a great deal. I did not know about the chemistry, the part, so that was fantastic to learn more about. I look forward to further discussion next year.
Excellent. Thank you very much, everyone.